we can start. First, I'll finish one little thing I didn't talk about on Tuesday, and that's applications of the theorem we proved. So we have this Rouchet theorem. So recall Rouchet theorem. So the Rouchet theorem basically tells us how to estimate behavior of complicated functions by some more elementary functions with satisfying some requirements. So we have two holomorphic functions, f and g, in some simply connected domain. And we have closed path gamma a b to the domain. So let's say simple closed path. And we have the estimate on the image of this path. We have that the difference between the functions is strictly less than sum of the values. Then f and g have the same number of zeros inside gamma, where I'm not commenting what inside means, but you should visually understand what it means. So you should think about the circle and the disk inside. Counted with multiplicities. So this is what we more or less proved in the previous lecture, and one application, another proof of the main theorem of algebra. Application. Another proof. Another, I would say, one line proof. Of the main theorem of algebra. So here is the proof. So we need to prove that any polynomial, so want to prove for any f of z being, let me make it make the leading coefficient equal to 1. Has zeros in complex numbers. Yeah. So f is chosen. So we want to apply Euclid theorem. So f is chosen, g of z is simply z to the n. Then 0 is the root, so 0 of g of z with multiplicity n. So the number we're talking about is n, and now take g of z, or maybe f of z, minus g of z. I mean, we need to check that the conditions of theorem is satisfied. So our g will be basically all complex numbers. Now we need to choose gamma. So the difference is the rest of the expression. So then estimate. So let's take gamma to be a large circle. Say gamma is dk of 0 r, where r is very big. So let's, I mean, the actual estimate will come, of course, from f itself, but the point is that absolute value of f of z minus g of z is estimated by some and we want to compare this with something that is even smaller than the estimate, with simply absolute value of z to the power n. It's summoned in the right hand side. And you know, the limit for r going to infinity of divided by r to the n equals to 0. So in particular, I can choose r in such a way that this expression is strictly less than 1. Well, since it's less than 1, we immediately get that then absolute value of f of z minus g of z is less than r to the n, which is absolute value of z to the n is less or equal than so the conditions are satisfied. For this gamma. Yep. And apply the theorem, we get that f of z, which is this random polynomial of degree n, has n roots counted with multiplicities. In K0 R. And that's what we want to do. Good, so that's what we finished with today's with yesterday's material, and Tuesday's material. And now we'll talk about applications of this Cauchy residue theorem. So, if you remember, the theorem itself says the application. Residue theorem. So the theorem itself said that G is connected, and gamma simple closed path inside it. So surrounding singularities of f, which was a function from G minus a few points. So numbers, holomorphic. Then the 1 over 2 pi I integral over gamma of f z is sum of residues of f and ai. So notice that all these singularities are isolated. In particular, this means that there are finitely many of these points. Now, here is how we apply the so two types of application. So first type is when we have some real valued function on the real axis. On R, and then we express integral from minus infinity to infinity f of x dx, understood as limit for r tending to infinity, integral from minus r to r f of x dx. Via residues of related meromorphic function. Related function on C, so with singularities. So there'll be a few examples along these lines in the book, and more in your final exercise. And second type is the opposite. So imagine that you need to take a sum of some expression. So there are two types of expressions. So one type is sum from n equal minus infinity to infinity f of n for some function. And the second type of expression is sum from n equal minus infinity to infinity minus 1 to the n f of n. And we want to make sense of these series, and both are understood as limits. So as before, so this is the sum, the limit for n m going to infinity, sum k equal minus n to m f of k. So these are finite sums, and this one is understood in the same way. So n m going to infinity, sum k equal minus n to m minus 1 to the k f of k. So it will turn out that there is a method in some cases. So there's a method to express both of them as integrals, and then the question is how to evaluate these integrals. So a certain integral over gamma of something. So in a way, limit over n m gamma n m, again limit n m gamma n m. So these sums will turn out to be residues. So in a way, here we read the theorem forwards. So we start from the integral and then evaluate it via residues. And here we read it backwards. We start from residues, which we want to evaluate, and evaluate it via the integral. So, so this will be summation of series, and this will be evaluation of real integrals on the real axis. Let's pass to examples. So this was like general discussion. Let's pass to examples. So, first example I want to talk about is, yeah. So this is the first topic. We're talking about the integral from minus infinity to infinity, x squared plus 1 squared dx. And we want to evaluate it as a definite integral. So here is the picture. So we agreed that this is the limit for r going to infinity, integral minus r to r, x squared plus 1 squared dx. So I'll write the method. So you draw this integral on the axis. So this is the real axis. And we're integrating from minus r to r. And we have a nice function which is a restriction of holomorphic or meromorphic function. is restriction of z squared plus 1 squared to real axis. So first thing to do is complete this interval from minus r to r to closed path in such a way that first I'll draw, but then I'll choose such completion. So I'll just do something like this. In such a way, so this is my original one, so call it gamma r, and this will be gamma additional. In such a way that the integral of, so this is f of z dz over gamma ad is small, depending on r. Which means that you can do it uniformly for all values of r in such a way that this will tend to 0 when r goes to infinity. Now, then find singularities of f of z inside gamma, which is gamma r union with gamma ad, somewhere here, and actually hope that there are no singularities on gamma itself. Yeah, and then apply Cauchy-Rezvi theorem. By finding residues in singularities. So then we'll get, and pass r going to infinity. So when r goes to infinity, we'll get limit r going to infinity integral over gamma r f of z dz. This is exactly our integral from minus infinity to infinity of our function, plus limit r going to infinity integral of gamma ad f of z dz. And we agreed that we have made it small, so it's 0. And then this will be 2 pi I times sum of residues. So that's how we do it in general. So I'll complete this program for this particular function, of course, in a little while, but just one warning, which is a typical thing which happens, especially if you are in a hurry or making arithmetic mistakes. So the warning is that this integral, whatever it is, f of x dx is a real number, so beware of answers complex numbers. So when you evaluate these residues, of course, a priori you can get random complex numbers, but the question is in real numbers, so the answer should also be in real numbers. And if suddenly you're integrating some real valued function on this real line and get, say, 3i, this will be definitely a problem. But so let's apply this program in particular case. So first thing to do is to, I mean, it's like with any integration, you make a lucky guess. So lucky guess. So our function f of x is x squared plus 1 squared. So lucky guess. Of this additional path. So we have minus r, 0, r complete the path by half circle. So my gamma ad is just this half circle. Now, so look at the function. So f of z is z squared plus 1 squared. So then singularity. So the only singularity is singularity of f of z. And that's a pole at. So you need to solve the equation z squared plus 1 squared equals to 0. So in other words, z squared plus 1 equals to 0. And we are interested, so the answer is z is plus minus I, but only one of these is inside my curve, and that's I. So z equals to I. And then you can find the expansion. So of z squared plus 1 squared at the point I. So I won't even n times this will be. I'll just write the answer. You can see the calculation in the book. I don't want to do it because there are more examples. Is just pi over 2. Now we see that this does not depend on r. So limit for r going to infinity of right hand side of the theorem is pi over 2, and happily it's a real number, which is very good. Otherwise we would suspect that either something is wrong or the estimate for this integral is not 0 as we would like to have it. Now, so gamma ad r squared, sorry, of z squared z squared plus 1 squared dz. So this function is simply, so we want to estimate it. And we know the estimate. So supremum of on this half circle times the length of gamma ad. So the length is clear. This is half circle, so the length is pi r. Now the estimate for this is, of course, the denominator has higher power than numerator, so the estimate is r squared plus 1 squared. And so the argument of that is between 0 and pi. So then this is less or equal than r squared times r squared plus 1 squared. So the exponent of numerator is 3, and the exponent of denominator is 4. The top degree here is 4. So then the limit of this, so when r going to infinity, integral of gamma ad z squared plus 1 squared dz is simply 0. So we're lucky. This means that limit for r going to infinity, integral from minus r to r x squared plus 1 squared dx equals, in fact, bless you, so integral over gamma, so limit r going to infinity, z squared plus 1 squared dz, and this is the residue, and this equals pi over 2, and that's the answer. So, this is exactly, on the other hand, this equals so what you immediately notice is that when you want to do this for polynomial, so in this case we see that this is a remark. Degree of the numerator minus degree of denominator is minus 2. So, and this actually what helped us, because if you look at the estimate above, we of course have numerator and denominator, but also we have the length of this half circle, where we have another power of r. So so in particular, if we had for f of x being, say, x cubed over x squared plus 1 squared. We would try to do a similar thing, but the estimate above would fail, because instead of r cubed over r squared plus 1 squared, we would have r to the 4 divided by r squared plus 1 squared. And this would, so the estimate for gamma odd would fail, would have failed. So, to this end, let me formulate a theorem which basically makes this observation a general statement. In general, for f of x being p of x divided by q of x, these are polynomials with degree of p less or equal than degree of q minus 2. That's exactly our estimate. Then integral from minus infinity to infinity f of x dx is 2 pi I sum of residues of f of z in upper half plane yeah. I mean singular f at aj. And the explanation is so proof, or maybe hint of proof. So just like in the previous calculation, so we need to estimate, so choose gamma odd to be this half circle, like this. So, and then we need to see that integral over this gamma odd f of z dz tends to 0 when r going to infinity. And this is exactly the calculation above. So almost done. I'll just modify this. So this will be my p of z, q of z. Yeah, same. P of z, q of z. Yeah. So subtract of times pi r. So on z in gamma I. So this part, as before, has a limit equal to 0, and so the whole thing will be estimated by some constant times pi r times 1 over r squared. So this r squared comes exactly from the difference of degrees of numerator and denominator. Good. Let's make the break. Then there are several more examples to consider. I'll pay attention to one calculation in part 1 and one summation of series. So both types of problems are in the final exercise.